Hello. In our last discussion, in the last lecture video, we have explored the dynamic programming and MDP and their application in reinforcement learning. Now, in this video, we'll extend the discussion to implement the MDP and the programming with Python code to represent a grid world problem, normal grid world problem, how the decision making is being generated. The decisions are being generated to take the actions. Various actions are decided, or the decisions regarding the actions are taken according to by following the MDP rules and the dynamic programming process. So, as we just brush up the previous sessions lessons that we have discussed already in the previous video, there are the gist that we have. That is a value function. There are two major aspects we had: the value function, the state value function, and the action value function. State value function is often referred as a value function. The action value function is often referred as a Q function. So the is a recursively updated according to the Bellman equation like this. We have the value function is updated by this formula, mathematical formula. We have this Bellman equation, and this will go on till the optimality is established. So this is for value function also, and for state the action value function as well. That is a Q function. So the major three outcomes we have. One is the optimal value. One is the optimal value function, that is V star S. Second is the optimal Q value function, that is Q star S A. That is a Q star. That is the optimal action value function, which is a function of state and action both for a given state action that we have already discussed in the last video. And also the optimized policy. The policy is optimized, the optimal policy, that we have to find the best policy after the policy evaluation and policy improvement. So these are the equations we have typically used in the program. That is the policy evaluation stands with this particular mathematical rule. The policy is evaluated. The value function according to a certain policy pi is equal to summation over all actions, the probability of action given the current state, multiplied by the summation over all next states, the probability of the next state given the current state and the action, multiplied by the total outcome of the current state or immediate reward, okay, after transition from S to S prime, and the discounted value of the value function according to the value function belongs to the policy itself. That value function is of the next state S prime. So discounted value of that plus the current immediate reward that the agent is achieved by having a transition from S to S prime, multiplied by the probability that the degree of chance, the degree of possibilities that the agent will have a transition at all to the state S prime. This total product represents the likelihood score, or we can say the likelihood score of the state transition to S prime, or the likelihood score after having the transition from the current state S to the next state S prime by taking action A. So these are the total return of the current state and the next state, the total return multiplied by the probability itself. The probability defines the possibility itself for transiting to the next state S prime. And that is for all S prime, we are adding up this particular estimate and multiplied by the probability of action given the current state. And that will be added with all for all actions, finally give the total value function. Okay, the policy value under the policy, the total value function under the policy pi. So this is typically equal to this, that pi A given S into Q of pi given S and A. Q is a Q value function under the policy, which is a function of current state and action. Okay, multiplied by the probability that the action is taken. Okay, so the product again, it is required to be explained. This product again represents the actual score, the actual potentiality of the current state if action A is chosen. This is a score, the expected value, the expected Q value, if the action A is chosen, and this is the probability of that the action is chosen. Okay, this product will tell that what is the actual value we should estimate. And that will be added for all actions. We'll give the total value function of the current state S. That we have already done. That's under the policy. Now we have the policy, and policy, we can improve this policy by taking the maximum of this. By taking the maximum of this, by for a certain action A, this particular value function under the policy goes to its maximum, goes to its highest value, goes to its maximum value for a certain value of action, certain action. For a particular action, this particular argument, that summation over S prime or probability of S prime given S and A, current state and action, multiplied by the total return of the current state as well as the next state. Okay. So this is the maximum value will be chosen. The action will be chosen that will uh, that will generate the maximum value of this internal, that is Q function. It is actually a Q function we can have. Okay. The action will be chosen that will maximize the Q function. This summation is a Q function. So this is a policy improvement. And the policy improvement, policy evaluation taken together, we can say policy evaluation. And policy evaluation, policy iteration, I'm sorry, the policy iteration includes policy evaluation and policy improvement, these two sub steps. Okay. And after that, the Bellman equation, according to the Bellman optimality equation, the value function is updated. The optimal value function is derived by choosing the maximum action. Okay, by choosing the maximum action and corresponding the total Q value, the total Q value for all the next states. Okay, for all the next states for a certain action. Okay, for a certain, or otherwise, we can say for a certain action, this total summation, that is a Q value, goes to its maximum. For a certain action, this summation part, that's a Q value that goes its maximum. That particular action will be chosen. Okay, that particular action value will be chosen to derive the optimal value function or improved value function. Okay, updated value function, whatever we can say. So, so our main motto is to find three outputs. One is the updated optimal policy, optimal value function, optimal action value function. Again, optimal state value function, optimal action value function, and optimal policy. How to derive this? So let's open with the Python program. So it's a grid world problem, having some decisions as output, is generating decisions as output. So we have defined four states. In the first line, we are defining four states, S1, S2, S3, S4. We are defining two actions, A1 and A2. There are four states and two actions. Current state and next state are definitely, they, both of them belongs to this set of states, which is called, often called a state space. And this is called action space that contains two actions. Those two actions are belonging to the action space. And we have the P. This means transition probability is already given. So Markov decision process, along with dynamic programming, assumes that the action probabilities or transition probabilities are given. The action probabilities and transition probabilities are given. These are transition probability. Means for a certain value of current state and action, what is the probability that the agent will have a transition to the next state? These probability schedules are given as assumed. Okay. So those are given. Like for example, it is all two 4x4 matrices. Let's clarify these very shortly. Four states are there. Each of four states will have a transition to again the four states, same states. S1 to S1, S1 to S2, S1 to S3, S1 to S4 in this way, S2 to S1, S2 to S2, S2 to S3, S2 to S4. So four states are mutually all to all is a Cartesian product type combination. We have is an all to all combination for current state and next state. Both belongs to S1, S2, S3, S4. So we have 4 into 4, 16 combination. And this first matrix, first 4 by 4 matrix is for one action, that is action one, that is A1. So whenever we are in state one, for example, we are in state one, the agent is in state one, agent takes the action A1, okay, the transition probability to S1 itself, self to self transition means no transition at all. There is no state transition. If the agent is in state one, takes the action A1, no transition means state one to state one, transition probability is 0.7. So 0.7 probability is there that the agent will have no transition. Similarly, we have in the second part, that second value that is 0.3. That is the if the agent is in state one, takes the action A1, what is the probability of the agent to have a transition to S2? That is 0.3. So agent is having 0.3 probability to have a transition to the state 2 if the action 1 is taken, A1 is taken. In this way, we have S1 to S1, S1 to S2, S1 to S3, S1 to S4. All the transition probabilities by taking first action is mapped here as given. These values are given. Similarly, for action 2, if state 1 is taking action 2, and the probability that the transition will be to state 1 itself, this means there is no transition, sticking to the same state, that is 0, 0, is sticking to the same state that is 0. Probability 0. There is no probability, means 0 probability. It's impossible. If the agent is in state 1 taking action 2, it is impossible to stick in state 1 itself. It is impossible to stay at state 1. Similarly, if the agent is in state 1, is taking action 2, there is no probability of having transition to state 2. There is 0.5 probability of transiting to state 3. There is 0.5 probability in transiting to state 4. In this way, the state 2, starting from state 2, second episode. So assuming state 2 as the current state, if the action 2 is taken, what is the probability that agent will have a transition to state 1? That is 0. So there is no probability. It's an impossible event. If the agent is on state 2, if agent takes the action 2, there is 0 probability that the agent will have a transition to state 1. Similarly, 0.6 probability that the agent will stick at state 2 itself without any transition. The 0.4 probability the agent will have a transition to state 3, and 0 probability again, the agent will have a probability in going to state 4, in having a transition to state 4. In this way, we have two 4 by 4 matrices that will represent state to state transition among these 4 states by taking 2 actions. So actually 4 by 4 multiplied by 2. It is two 4 by 4 matrices we have. Now reward. Reward is also two 4 by 4 matrices. Same thing. The reward, the R is initialized by this value. If state 1, state 2, state 3, state 4, we are having the present state. And we are having the next state also, state 1, state 2, state 3, state 4. So present state is also, present state also belongs to state 1 to state 4. Next state also belongs to state 1 to state 4. So first one we have the reward 0.5. If the agent is having a transition, agent is on state 1, is having a transition to state 1 itself, means no transition at all by taking action 1. If by taking action 1, there is no transition, then reward 0.5 will be earned. Because it's a desirable. It indicates it is desirable. By taking action 1, the agent should not have a transition to the next state. So the reward point is 5. Second one, if agent is in state 1, agent takes the action 1, action A1, wants to have a, and what is the probability of having a transition? Okay, that is a probability is given. That is 0.3 already. Next state, if the action 1 is taken, A1 is taken, the agent is on state 1, agent is having a transition to the next state S2, then the 0 reward is earned. This means it is undesirable. From state 1 to state 2 transition is undesirable from these indicates. These values indicating these. Suppose, for example, this particular 4, if I concentrate on this 4 that I highlighted here, this means if the agent is on state 2, taking action 2, it's a second matrix, it's a second set of matrix, is taking action 2. The agent is on state 2, taking action 2. And if the agent is having a transition to state 3, then the agent is going to earn the reward point of 4. Means it is quite desirable. In this way, the reward combinations are given to indicate its desirability. So this is the way we have to understand the matrices first. Next, we have the value function initialized by zeros. Value function is a series of value. It's a vector. It's not a single value. It's not a variable. It must be a array variable. That's why it is implemented with NumPy. Q is also the array variable, which is a vector itself. Okay. So those are the dimensional vectors we have. The threshold means the minimum floor limit. Okay. A 5 means 10 to the power minus 5. We can have 10 to the power minus 4 also. That is the lowest point till which the loop will go. 10 to the power minus 4 means 0.0001. So this is the lowest value. The threshold is having that value. That is the lowest point till which the loop will execute. Delta means the difference. It is just declared the delta as a, okay, so integer. Now iteration, a variable that initializes with 0, and delta, if delta greater than threshold. Okay. Now delta is greater than threshold. So long as delta will remain greater than threshold, the loop will continue to execute. The delta will beginning with initialize with 0. The delta initializes with 0. Okay. And new value function equal to np dot zeros like v. This means a new instance of the value function is created here, and that is definitely initialized by zeros at the beginning. Now the second system of loop will start for s in range link states. Now the loop is started that will traverse from one state to another. The traverse along the states. Now Q is the Q value function, that is we can action value function initialize with blank. Okay. The state value function, action value function or Q function initialize with blank. Okay. Now first of all, the Q values for each action we will derive, and we will take the maximum Q value to derive the state value function as per the theoretical part we have learned. So we have these for A in range actions. Under each state, there are a lot of actions. Okay, a particular state, if an agent stays at current state, there is a numerous options of actions the agent can take. Value will be, now we are representing the Bellman equation by this line. This is a Bellman equation. Sum of, okay, that is a transition probability. We have probability S next, probability that the agent is having a transition to the next state, S next, given the current state, when it's given, when it's assumed that the current state S and A is given, conditional probability completely, multiplied by the reward earned if the agent has a transition to the next state S next, having the current state S and taking action A, plus the discounted value of the value function of the next state. So this total sum, R plus V, R plus gamma into V, this total part actually represents the return for the next state and the total return of the next current state and the immediate next state. And that is discounted by, that is actually multiplied by this sum of, multiplied by the probability that the next state will be, the agent will have a transition to next state. So this is the effective score, or we can say this is an effective score the agent can have, the sum of all these things for all. Okay. The sum for all actions, we get the value. Okay. Sum for all actions for each action, because it is under the loop of action E. So sum of all these values for all actions, we are summing up these value estimates, this value probability of next state multiplied by the total reward, that is to be total return that is to be earned, okay, by going to the next state, multiplied by the probability of the next state, the probability that the agent will have a transition to next state. This means actual effective value the agent is going to get if the agent is having a transition to is next. Okay, and it will be summed for all actions. It will be summed for all actions, and that is constituting the value function. Okay. Next, under this value function, under this A, that's the action loop, we are having the state loop itself. For S next, now the action is derived for all. For each action, we are giving the sum, the value function counting the sum. And for each action, we are deriving the Q function, each every step. This is a Q function, and sum of all Q functions give the value functions. Now we have under the A loop, we have the X next. For all next states, we are having this loop. One next state, second next state, third next state. Okay. The action, for all actions, we are having this. For a certain action, we are having this particular sum. Okay. For some action, we are having this particular sum. Okay. Probability of this multiplied by this, multiplied by reward plus discounted value of the next value function. So we are summing up all these things under which we are having the x next. Exactly, it is representing the equation what we had. Exactly, it is representing the equation. Okay. See here is the update equations. It's all represent the update equations, as you can recall. Now, after this is being done, then we have the Q value function is assigned by the value. The value that is derived, that value is actually a Q value we have. That value is actually a Q value. For a certain action, given action, we are having the sum of all these values. That is actually a Q value. The Q value is nothing but this particular value is generated. Now for S next, for every next state, we are having the Q value. For all next states, after the loop is ended, okay, now we are having these Q values. Now for X next in range, then states, we are having the particular loop for all the next states. Exactly the equation which is followed here. Just see, just look at the equation here. State value function. We are having state value function for all actions. We are adding up this particular product, the multiplication. The probability, the action probability, when the current state is given, multiplied by the summation, the sum over all the next states, the probability of next state multiplied by the potential return that is going to be earned till the next state. Okay. So this is the total value we have for all the next states by taking state and action. And this is the probability that at all the action A is chosen. Okay. So this is a Q value. This is a Q value. And Q values are summed over all actions to get the value function. So the internal one is the Q value. And when it's summed over all actions, it becomes the value function. So exactly the same thing here that is represented here. There's a Q value. This is a Q value. This is a Q value. Absolutely, this is a Q value. And again, we brush up the Q value, just relate with the code theory, the formula. What is a Q value? See, this summation part, this sum, that is a Q value. This is a Q value. Summation of all the next states. Summation over all the next states. We are adding up the probability of the next state multiplied by the total return that is going to be earned till the next state. And that is added for all the next states. So that will definitely bring you the Q function or action value function. This part is a Q function. And that is the value itself, which is referred in the program by the variable called value. That is the action value function. The action value, the total action value, or we can say Q value. And this QSA is assigned by the value. Just see here, QSA is assigned by the value. And we have the QS. The Q is a array. The Q is an array. And the array will be inserted by those values one by one. Okay. QS.append. So we are having these values one by one to be appended. QSA is a Q value, and this particular QS is a array itself that is being appended by these values. Now, for example, that is for all state. The loop is written in the next line of this. Actually, under this loop is working with this particular line. Okay. For all A's, this particular sum will have. We'll have for all states, we have this particular sum. This sum is for all states. This sum is meant for all states. This is a sum which is meant for all states, as we can comfortably see by these two lines. For all states. Now we are having this particular value to be assigned as a Q value. Now, after the end of this loop, when for all the actions, we have traversed all the actions. We have traversed all the actions. We got all the separate Q values for separate actions. Suppose there are n number of actions. So n number of Q values we got after the end of the loop, and among which we take the maximum Q value. The maximum Q value as the new value function. The maximum Q value, we take the new value function. Taking all the actions together to get the maximum Q value is the new value function, and delta will be the difference. That is the temporal difference, or we can say the difference which is mapped here. Same concept of temporal difference is there. That is the max of delta and the absolute value of new value function and the current value function. So new value function is the desired one, current value function, the reality, the gap between them, and the delta itself. If the current value of delta and this difference, whichever is lesser, that will become the delta. The delta, the difference, that is a temporal difference or normal difference, whatever can be assumed. That delta will be assigned by the value of the lower difference. That is whichever is lower, either current delta or the difference between the new value function and the current value function, this difference, temporal difference. Okay. So we are having the delta. Delta we define as lower between, the delta will decrease gradually. Okay, delta will choose the lower one among them, and gradually the delta, the difference will go on decreasing. And our objective to vanish that particular difference. We have to be that the difference has to come closer to zero. Then the difference come closer to zero means the reality meets the target. The reality meets the expectation. So this means the difference is going to be minimized, and difference is tending to zero means the difference between the reality and the expectation of the target, it is tending towards zero. That is a desirable solution that we can have. Now V equal to new V dot copy. V the value function, capital V. Iteration will be one step ahead. So we have the got value function. The policy we have the argmax. Okay. Argument maximize of Q. We will choose the action that will maximize Q, that is argmax. That also we have got in the PPTs in the past lecture video and this lecture video also. The argmax, that maximize the A, it will choose the action A that will maximize the argument. Which is the argument? That is Q. That is a policy evaluation. That is a policy improvement, or we can say optimal policy. It's the optimal policy what we have. So optimal policy, we have got it. For a maximized Q value, whatever actions is responsible to derive the maximized Q value, that particular action will be chosen and will be included in the policy. The policy will be assigned by that action which is going to maximize this Q value. Okay. After these particular Q values, all Q values are derived within this loop frame. After that, the maximum Q value will be assigned as a value function, and the policy will take that action which is responsible to maximize that Q value. Policy is concerned about the action. The value function takes the maximum Q value over all actions by taking all actions. So that is the value function. Okay. And we have this is a value function, optimized value function, that is new value function. Normal value function is the sum over all actions. And this is an optimized value function, the max of this. And delta is the difference that is going to be minimized in every step. And minimization of delta is the objective of our process, MDP process, and applied in RL. Finally, we are printing the value function, that is V, that is the optimal value function. Q is the, which is the QSA, that Q Q is the optimal state action value function. V is the optimal state value function or normal value function. Q is the optimal action value function or Q function, optimal Q function. And we are printing out the policy. For S and A in enumerate policy, okay, S and A, the enumerate function, we have the SA. For each SA, for each current state and action, we are printing the policy. Okay. State X takes action A. Policy is a combination of state and action. From which state to which action to be taken? From which state, which action is most desirable? Which action is most profitable? Which action is most beneficial to be taken? That decision is the policy. That is the policy. And that is completely probabilistic. So this is the output that we can have. First of all, we have the state value functions. There are four state value functions we have. How four state value function means why there are four state value functions. Why that is because we are actually the state value function assumes all actions. Okay, action one and action two. So first of all, there are four actions. There are four states. State value function. There are four states undoubtedly. Okay. Now state one to state two transition. State one to state one transition. That is the value function. Okay. Optimal state value function. State 1 to state 2, this is the optimal state value function. State 1 to state 3, state 1 to state 4. So those are the typical value functions we have. Those are the typical value functions what we have. Typical value functions what we have. That is state 1 and state 2, state 1 and state 1 to state 1, state 1 to state 2, state 1 to state 3. So whatever actions, among the best action is assumed to be chosen, which is maximize the Q value. And that is the value function that we are going to take. This one. Optimal action value function. Just see here. This is for state 1 to state 1 transition if action 1 is applied. The action value or Q value, if the action 1 is applied and there is a transition for state 1 to state 1, that is the Q value or action value. And same from state 1 to state 1 transition, if we use action 2, this is a Q value. Same thing for the next state, S2. S2 to S1 transition, if we consider the transition from S2 to S1 and we apply the action 1, this is the Q value that is going to be earned. And same thing, if the agent is on state 2, agent has a transition to state 2 itself, means there is no transition at all. Then if the action A2 is chosen, action 2 is chosen and no transition at all, then this is the Q value function, optimal state value function is achieved. So there is actually 4 by 2 matrices. Why 4 by 2 matrices? Because there are two actions. So for each state, we are having the two actions. Okay, each state. First state to each state, current state, next state combination, we are having each current state, next state combination. This is one current state, next state combination. Okay, S1 to S2, S1 to S1, S1 to S2. So S1 to S1 combination, we are having the action 1. So state 1 to state 1 combination, we are having action 1. State 1 to state 1 combination, by taking the action 1, this is a Q value generated. Okay, state 1 to state 2, by taking action, by state 1 to state 1, by taking action, same action 1, we are having generating this Q value function. So in this way, for state 1 to state 1, action 1, state 1 to state 1, action 2, state 1 to state 2, action 1, state 1 to state 2, action 2, state 1 to state 3, then same thing, we are having this, the same way we are having these 4 by 2 matrix as we have for 4 states and 2 actions. So optimal state action value function. So action value function typically sums all from state 1 to state 1, state 1 to state 2, state 1 to state 3, state 1 to state 4. From state one, transition to all the next states by taking action one. Whatever value, action value we are generating, we will add. And this is the sum of all the action values, assuming S1 as the current state and A1 is the action chosen. A1 is the action chosen. Similarly, if S1 is the current state, the total sum of all the values for transiting to all the next states by taking action 2, if the current state is state 1 and current action taken is action 2, the current state is fixed at state 1, the action taken is fixed at action 2. So we are having this is a total sum of value that is generated to have the transition from all the next states. Similarly, when the state 2 is the current state, state 2 is the current state, and in order to transition to other states like state 1, state 2, state 3, state 4, all the four states, okay, by taking action 1. So this is the total sum of all the values that is going to be generated. So those are the Q values. And the value function is nothing but the maximum Q value for each action, both actions. Suppose, for example, for state 1 to state 1 transition, for state 1 to state 1 transition, you see, by taking action, the Q value generated is 59.95. And by taking action 2, the Q value generated is 63.65. So it's a better one because it gets a better Q value. This means it is better in terms of the goal, in terms of the objective. So definitely this one will be chosen as the value function. So first one, 63.65 chosen. For the second pair, we have for action 1 and action 2, definitely action 2 is more beneficial. So it will give the 60.58. So definitely 60.58. But in the third state, assuming the third state as the starting state, in the third episode, what we can say, the first action is more beneficial and it gives the more Q value, that is 67. It is chosen as the value function 67. Similarly, for the fourth state as a starting state, the second action is more profitable. It gives the 62 as a Q value, will be chosen as the state value function as the same 62.3719 and so and so. So this is the way we can execute the program. And this is the way the MDP and dynamic programming is used in reinforcement learning and implemented in a Python program. And this is the base of creating a game using the grid world. Thank you so much.